In this video, I'll discuss about correlation. Correlation is a statistic that we compute to find a relation between two or more variables. So this is basically a bivariate concept. There is multivariate correlation as well, but we'll keep it to bivariate at this point. So how do we see the relationship between two variables? One way of doing it is we plot the two variables. Okay. So which plot do we use? We use scatter plot for that. Okay. So looking at the scatter plot, we can find what type of relationship exists between two different variables. So it gives us an idea like whether there is a positive relationship, negative relationship, direct relationship, indirect relationship, but we actually can't quantify it just by looking at the scatter plot. So how do we quantify the relationship? Correlation is the statistic used for quantification purpose. So we can measure the strength of the association between two variables by finding out correlation statistics. Okay. So one of the feature of correlation is that it gives us the strength of the relationship between two variables, how well they are related to each other. Okay. So two variables having high correlation are highly correlated, or they are strongly correlated. They have a very they are very close to each other. One moves with the other. And one thing to remember here is that there is no causal impact, in the sense that if two variables are correlated, they may not cause each other. Okay, so no causal inference can be drawn by looking at only the correlation value. So what is causal inference? If one causes the other, if x and y are two variables, and if I can say that x causes y, then there is a causal relationship between x to y. Similarly, if y causes x, there is a causal relationship between y to x. So there can be situations where x and y are highly correlated, or there is a strong relationship between them, but neither of them cause the other. Or in some cases, one causes the other, but others doesn't cause the first one, or x causes y doesn't cause x. So these possibilities can be there, or x causes y causes x. This can also be a possibility, but there cannot be any guarantee. Just looking at correlations. So in short, correlation doesn't really guarantee causation. So couple of plots we have. So these are the scatter plots. In the first graph, you can see the pointer. There is a strong relationship between x and y. So as x is increased, y is also increasing accordingly. If x is increasing, y is increasing, right? So we can say that there is a positive relationship between x and y, right? If I go down below, if x is increasing, y is actually decreasing, right? Here, if I take the first circle, you can see the value of x is very less, but the y value is very high. If I go down, here the value of x is very high, but the value of y is very less. So there is an indirect relationship between x and y. Okay. If I go to the third plot, you have a relationship, direct relationship to some extent, then there is indirect relationship. So initially there is there is a direct relationship, positive relationship till one point. Till this point, y increases with respect to x, but after that y decreases. So this kind of relationship where it's not a linear relationship, we call it as curvilinear relationship. Okay, so it could be some kind of a curve, right? It could be parabolic, it could be hyperbolic, bolic, or that kind of a relationship, or circular. It can be anything. So it's not something that is like a straight line. Here you can plot a straight line, that passes through the points. Even in the second graph we can plot a straight line that passes through the points, but here it's very difficult to draw a straight line that passes through all the points. Similarly, in the fourth graph, another way of representing a curvilinear relationship, you can see it increases with a very slow rate, again increases at a very fast rate. So the slope is changing after one point. After this point, the slope is changing at a very faster rate. So how is the relationship? Like here, the direct relationship, again it continues, it doesn't change, the relationship doesn't change, but the slope is changing, the strength of relationship is actually changing, right? So that's how we can interpret the scatter plot. But scatter plot is not enough. As I said, correlation is the one that will measure the strength of relationship between two variables. Okay. As I said, there is a strong relationship between. As I, in the last slide, we saw that how direct relationship and indirect relationship can be. We can take inference out of by looking at the graph. If x increases and y increases, there is a direct relationship or positive relationship. If x increases and y decreases, then there is indirect or negative relationship between the two variables. Here there is a direct relationship. If I go to the second graph in the right side, there is also direct relationship. But what is the difference between these two graphs? In the first one, there is a strong relationship between the variables x1, y. Whereas in the second graph, there is comparatively weaker relationship, or there is relatively very weak relationship between x and y. Similarly, the graph that I am pointing to has a negative relationship, but the relationship is very strong. Where the fourth graph or the fourth plot is having a weak relationship between x and y. So if our data points are very spread, so we can say that the relationship between the two variables are are relatively weaker. So there can be cases where it's circular in nature, then we can say that there is absolutely no relationship between x and y. Okay, or sometimes the points are parallel to either x-axis or y-axis. As you can see in the second one, the circles are all lying on a line which is parallel to x-axis. So if we change x, there is hardly any change in the y value. So in such scenarios, we can say that there is hardly any relationship between x and y. So correlation coefficient is the statistic that is used to measure the strength of association between two variables. Okay. So generally it is noted, it is denoted by R and rho. So if we were using sample, then it is denoted as rho, and if we are computing the correlation of population, then we denote it as R. or did I say the ulta? Sorry. So the sample correlation is R, and the population correlation is rho. Okay, so it's the opposite. The population correlation is rho, and the sample correlation is R. Okay. So what are the common features of rho and R? Not to be confused with rho and R. It actually depends whether we have taken a sample data or a population data. Okay, so most cases we actually use sample data. So most of the cases it will be denoted as rho. So the correlation coefficient is actually unit free. There is no unit. So if you do any transformation of the variable, and you do the similar transformation of the two variables, there is hardly going to be any change. For example, if you standardize the variable x and y and take the correlation coefficient, and you take the correlation coefficient without standardizing it, it's going to be the same. So it's not going to change. It's unit free. It lies between -1 to 1. If it lies closer to -1, then there is a strong negative linear relationship. If it lies closer to +1, then there is a strong positive linear relationship between the two variables. If it is close to 0, then there is hardly any relationship, or we can say that the correlation is very weak. There is absolutely no correlation if the correlation coefficient is 0. So the plots have been given here. There is an approximation of the correlation coefficient value. If you have perfectly, all the points are lying on a straight line, then we can say that either the correlation could be +1 or -1. So in the first graph, you can say points are lying on the line, but they are lying in a downward sloping path. So we can say that the relationship between x and y is negative, and hence the correlation is -1. But there is a perfect relationship, right? Similarly, if the points are lying in a parallel line, with respect to x-axis or y-axis. So in this particular graph, points are lying with parallel to the x-axis, but it could be the case that points could be lying parallel to y-axis as well. In both the cases, your correlation is 0. Okay. In the last one, you can see the points are lying on the same line, but there is a direct relationship between x and y. So your correlation is +1. Okay. And the other two graphs where the correlation is 0.6 and -0.6 and +0.3 are just the approximation. It could be anything. So we'll see how do we really measure this value accurately by looking at the data. Okay. So the formula to calculate correlation is given. You can see, like, x and y value are known to us. You will have a series of value for x, and you will have series of value for y. X bar is nothing but the mean, so you can always compute the mean of a series, and y bar is the mean of y. Okay, and this particular sign is the summation sign. So once you compute each of these values, you multiply them and take the summation. Similarly, you do the same thing here and then take the square root, and by using this formula you can compute the correlation coefficient. But there is an easier way in which we can compute correlations. So there is another formula which is derived from the parent formula, the first formula, but it's much easier while doing it by yourself. So if you are computing correlation, the best thing to use is the second formula. You can always compute the same thing using the first formula also, and you'll get to the same value, but second formula is what is recommended. So remember, here you have the n. N is the number of observations that you are having, and then x and y is known to you. So you can put it in the formula and then compute the value. So an example. So we have height of a tree and then diameter of its trunk. Okay, so height is taken as y and then diameter is taken as x. So first thing you do is that take the summation of that. So summation of y is 321, summation of x is 73. You multiply them and then again take the summation. You square them and take the summation. Okay, once you do that, you put these values in the formula. So that's all you need. Yes, so as you can see, you need summation of xy, summation of x and summation of y separately, and then you also need summation of x square and summation of y square. So once you put this value, because we already calculated this value, just put it in the formula and finally you arrive at this answer. 0.886 is the correlation between x and y. So that's fairly close to 1. We can say that there's a strong positive linear association between x and y. So what does that mean? X, if you increase x, y also increases in a positive way, or it also increases in that direction. Okay, so they move in the same direction. X and y move in the same direction. You use Excel formula CORR, you will arrive at the the same output, same value. There could be a little bit of change after the 3 decimal point, but that will be pretty much same because of slight change in the way Excel computes it. Otherwise, it will be most of the times it will be same. So in the next video, we'll study about how to compute correlations and different types of correlation that is available to us using SAS, and we'll also study like how best we can make use of correlation while doing statistical modeling. And yes, so thanks.